So I want to introduce some of what's new in Flink 1.2 and give you some perspective on where perhaps things will be going in future releases. Maybe I can just get some idea of who's in the audience. I imagine for some of you, you're relatively new to Flink. Maybe a show of hands of most of you, okay. And some of you probably have some experience with Flink or some familiarity with it. Just a few, okay. Well, this talk is going to cover a fair bit of ground, but I will try to not assume too much. If something's confusing, feel free to interrupt me. Let's hold most of the questions for the end, but if you need some clarification, let me know. So I'm from Data Artisans. This is the company founded by the creators of the Apache Flink project, and we're also the providers of the D8 platform, which is a supported distribution of Flink. So this is what I want to talk to you about today. First, give you some overview of everything that's new in Flink 1.2, which was just released a couple of weeks ago. Then look more closely at two specific features, Queryable State and dynamic scaling. Talk about what those mean, and then talk about something that's mysteriously called Flip 6, and we'll see what that means a bit later. So when we looked about 6 months ago at the features we were thinking about for Flink 1.2, they roughly fell into these 4 categories. And the one at the top is the biggest because it's really what we were hearing most from the community, which was we need more support for operational issues. And then across the bottom, we see ecosystem. That means improving Flink's ability to connect other things. Update the connectors, add new connectors, give us Kafka 10 support, etc. In the middle on the bottom is broader audience, and that means let's expand the set of people who can use Flink. And the efforts we've done there are around adding better SQL support. And then the final topic is application features. So here's what we were considering for operations, quite a few things. Ecosystem, we were hearing a lot about adding Mesos support, broader audience, and application features. And here's what we ended up doing. So the ones in green are the ones that were executed on and delivered in Flink 1.2. And the ones in red, oh, it doesn't look green on there. It looks green on here. And the ones in red are the ones I'm going to talk about in some depth today. Let me say a few words about some of these, since I'm not going to have slides on all the other topics, but maybe a few words about what was new. So authentication, we added Kerberos support throughout the platform. We also added SSL so that there's encrypted connections between all the pieces of the framework if you want them. Let's see what else is interesting. EMC contributed Mesos support. We added some new connectors. There was quite a bit of work on the SQL support and the table API. And process function and async I/O are quite interesting in terms of being able to give you better low-level handles if you need to kind of compose things yourself to do interesting windowing, joins, things like that. If there's questions about these, maybe we can talk about them at the end. So queryable state. So the use case I have in mind to talk about with this is counting tweet impressions. So this is actually something we worked on with Twitter. And to give you an idea of the scale involved, so they're seeing something like 1 million tweet impressions per second. So that means, a tweet impression is someone looking at a specific tweet. And something like 100 million unique tweets being viewed per hour, or 450 million per day, I think. So their goal is to have low latency access to hourly aggregates of these numbers, so they can get an idea of which tweets are trending, which ads are working, all that kind of thing. And they'd like to have sort of in-flight access to the current hour's information. So how can we do that? So let's first review how we would do this with Hadoop. So this is a classic MapReduce solution. So what we probably have working for us are, say, log files rolling up in HDFS with hourly rollovers. Let's assume that's what's happening. And these events, so here I've shown ABCD. Those are the tweet IDs. And we're just doing a map reduce here. So there's a shuffle so that all of the, for any given tweet, all of its impressions show up in one of these reduce operators that's going to do the counting. And of course, there would be a lot more than, the parallelism would be a lot higher than 2. I think they use something like 100 machines for this. So we do the counting up, and then every hour we can take the counts that we've accumulated here and store them in Redis. Everybody with me? Yeah. Okay. So how would we do the same thing in Flink? Can actually be quite similar. We're more likely to use Kafka than HDFS, but that's an implementation detail. We're going to do the same mapping and reducing. The state will be accumulated in Flink window operators. And we can do the same thing. We can hourly write the accumulated data into Redis. So far this looks basically exactly the same. What's the advantage of doing this with Flink? A couple of things. So when we did this with Hadoop MapReduce, we had these hourly log files, and they were being rolled over probably by the clock on the machine doing the log aggregation. And so it's not the processing time is being that's being considered is the time when the impressions reached this infrastructure, not the time that the impression actually happened. So these impressions are coming all out of order into this system, and the aggregation we're doing with MapReduce is an impression comes in a minute after the hour, and it's being counted as this new hour, but it really probably happened in the previous hour. We don't really know. So there's some fuzziness around the time boundaries here. If it's hourly, maybe it's not too bad, but we don't really know. It's hard for us to know how we're doing. With Flink, we also get better recovery behavior. So if you're doing, so Twitter was actually doing daily processing of these tweet impressions because they couldn't get enough bandwidth to Redis to do it hourly, so they were doing it daily. And if the daily job died somewhere along doing its task, that was a problem because it took most of the day to run and load its results into Redis. So better recovery behavior can be quite important. It's also quite feasible in Flink to have finer-grained aggregates. Since we don't have this correctness issue around the hour boundary or the minute boundary, whatever, we can do, we can aggregate by minute, for example, if we want to. Now, how does Queryable State fit into this? So far we've achieved part of our goal. We've got a nice fault-tolerant way of accurately counting tweet impressions, but we haven't provided any way to give access to the current hour's information. If we want information about how many times has this particular tweet from Donald Trump been viewed in this hour, we can't really know it until the hour's up. So what we've realized is that in this part of our infrastructure, Flink already basically has a nice sharded key value store where it's aggregating these pairs of tweet ID and impression counts. If we just expose that through a web service, people can have what they want. So that's exactly what we've done in Flink 1.2. You can query this state that's held in these operators and do what you want with it. So what we imagine and what we've built is a query service that can, depending on what's needed, query Redis or whatever database you're using to hold the historical results, and query the live Flink operators to get the results in process, and merge them in the query service. So that's what Queryable State is about. So this is nice because we can have correct data available instantly. It's still reasonably simple. It's correct in the face of failures, and Flink isn't being expected to do anything more than hold the current Windows state, which is what it already was doing. The disadvantage of this solution is we do still need a separate key value store, and we need to have this query service off to the side that can mediate between the two sources of information. What may be interesting in the future is to think about using a stream processor like Flink as the sole source of data, use it as the database. And this is just like the previous picture, except we just throw Redis away and accumulate all the state in Flink. Now, whether you really want to do that or not depends on whether you're prepared to trust Flink in all the ways you trust a database. Are you ready to feel good about your backup strategy with Flink state? Are you ready to feel good about migrating state across new versions of Flink and so on? And those are all the operational issues that we are taking on and trying to work hard on making sure that people can have that confidence in the future. All right, that's the end of this first session of the talk. So if there's questions about this, I'd be happy to entertain them now.
When you have this only query service that just goes to Flink,
yeah.
Where would you store the data persistently?
So we have what we call state backends in Flink, and the persistent state backend that we use is RocksDB. And you can configure RocksDB to persist HDFS if you want, for example. Okay.
You mentioned that the MapReduce job took about 100 machines before.
Yeah, I think so. I may be misremembering the details.
How many machines do you need for the Flink?
I don't actually know.
Okay.
This whole exploration was done some time ago. I don't quite remember the details. I think it was, well, sorry, I don't know.
So this looks quite similar to Kafka Streams interactive queries. And with Kafka, I have to build my own RPC layer that knows which instance to query for what key.
Yes.
Is it the same in Flink? That I have to build it myself?
So actually, this is. Thank you. That's a good question. So the query client needs to talk to the Flink job manager, which has in it a state location service that can tell it which of the task managers holds the state for that key, and then it can query there. Yeah. Yeah. Sorry, I stopped a slide too soon, but that was a good question. So part of what makes it possible to do this with Flink is Flink exposes state as a first-class citizen in its architecture, and the state is fault-tolerant. We offer exactly once end-to-end processing semantics, so that's important if you're going to trust the state. The state is already partitioned or sharded, if you will, across the different instances, and the state is being continuously updated, not being incremented in sort of batches as many batches go through, but each event is affecting the state individually, and it's stored in RocksDB, so it's nice and scalable. Any more questions about Queryable State? So the Queryable State API is in a very early state. It's a bit clunky to work with at the moment. We realized that. We wanted to get it out there to let the community start to experiment with it and help us decide, let's decide together where this should go and what it should become. But we're pleased to get it into 1.2 and have people start to think about how to use it. All right. The rest of the talk, I want to talk about dynamic scaling, and this is going to come in two pieces. The work we did in 1.2 and then the work that's projected for 1.3 and beyond. So the challenge here is, as we think about supporting typical use cases where people have changing workloads, different times a day, the load is quite different. And currently with Flink, in Flink 1.1, there was no rescaling support. And so you were forced to commit all the resources you were going to provide to Flink sort of all the time, which has the unfortunate behavior that most of the time you're wasting resources and occasionally maybe you don't have quite enough. And you'd much rather be scaling dynamically as the workload varies. So how can we do that? What makes that challenging? How have we made that work? That's what I want to talk about. So if your Flink job is very simple, if it's for example, just doing filtering and mapping, so there's no state being held anywhere, then this is trivial. You can just give Flink more resources and it'll just work. Where this becomes challenging is if you have stateful jobs. Then you have to think about, if we've added another node, how do we redistribute the state so that everyone has something to do? Well, so a brief recap of state in Flink. In Flink, we have two kinds of state. We have what we call keyed state and non-keyed state. So first of all, what's keyed state? Keyed state is like what we were doing a minute ago with counting tweet impressions. There, the key was the tweet ID, and we were counting how many times we'd seen that tweet. Non-keyed state, a good example of that would be maybe the Kafka source implementation. So what a source has to do is keep track of the offset. So in the case of Kafka, you've got a partition offset pair, and that's what needs to be saved and restored if there's a failure, and that's what's meaningful about the state of the Kafka connector. So with non-keyed state, the state is only bound to an operator, and with keyed state, there's this combination of an operator and a key involved, because each value of the key has its own separate state value. So we have two different solutions for these two cases. And the problem we're solving again is, how do we repartition the state when we come up with either more or fewer resources than we had before? So in Flink 1.1, if you were worrying about state in this simple non-keyed situation, we have what's called the checkpointed interface, and it has two methods you have to implement. You implement a snapshot and a restore. Pretty straightforward. You save the value and you restore it. But in that case, the state is just this opaque blob that Flink has no visibility into and can't repartition at all because it doesn't know anything about it. So we changed the interface, and now what you work with is a list. And this is a list of pieces that are distinct enough that they can be redistributed. This is the basis for redistributing the state. So an example of how this works, here you can see we have the Kafka source. Here's 3 of these pairs of partition ID and offset. In Flink 1.1, this was a black box and we couldn't repartition it, but now we've split it up into separate pieces, and so we can easily, if we need to scale out, just do so, and if we need to scale in, we can do that too. So that's the story for non-keyed state. So that's pretty easy to work with. For keyed state, the story is a bit different. So here what we do is we divide the key space up into key groups. And every key is in exactly one group. It's always in that group. And then these key groups are the thing that we can shuffle around. We assign key groups to workers. So rescaling just means changing the key group assignment. So here these key groups are on this node, and these key groups are on this node, and then if we scale out, we can separate these two key groups across 2 nodes. So what's available in Flink 1.2 is manual rescaling. That means you take a save point, you save the complete state of your Flink job, and then you adjust the parallelism and you bring it back up. And it comes back up with either more or fewer resources and keeps going happily. Of course, where we want to get to is to really have true dynamics rescaling, so that if your cluster manager can autoscale, for example, you can take advantage of that. And that's going to be the next part of the talk, explaining how we're going to get there. Right. Any questions at this point about the current status of rescaling Flink jobs? Okay. Then flip 6. So flips are, that acronym stands for Flink Improvement Proposal. And this particular flip is a joint work with Alibaba and Data Artisans. Alibaba is the largest. They have the largest Flink clusters that I know of. They have thousands and thousands of Flink nodes in production. So they have a data center like that running Flink. In 1.1, Flink supported standalone clusters with our own native Flink cluster solution, which is very simplistic, and Flink-on-YARN. In Flink 1.2, EMC contributed Mesos support. But in all these cases, really all that's happening is you have a standalone Flink cluster running in YARN or a standalone Flink cluster running in Mesos. It's not the sort of, it's not able to take advantage of the dynamic resource allocation that really would be possible. So the goal with the cluster management work we're doing in Flip 6 is to be able to seamlessly take advantage of all the features available in all these different cluster frameworks. And and that's proven to be quite a challenge. So tell you a bit more about it. So looking at the mailing list and talking to customers that we know, these are all the ways that we know that Flink is used in production right now. It's quite a handful of different solutions. Some people are using Flink standalone in a cluster or on dedicated hardware or in the cloud. People are using Docker in various ways. Before there was Mesos support, people were using Mesos under YARN because they really wanted Mesos. Yeah, and I don't know what OSGI is, so don't ask, but somebody's using it. Now, one of the ways we can characterize these different cluster management solutions is who controls the resources. So let me explain what I mean here. So imagine what happens if you're running Flink and one of the worker machines dies. Who's responsible for noticing and doing something about it? In the case of this color in the middle, which I want to call green, but doesn't look so green up there, it's Flink that's responsible for noticing and doing something about it. And in these other cases, it's the cluster manager that's responsible for, it's YARN or Mesos or whoever is responsible for doing something about it. That already makes things a bit complicated for us because that means that Flink has to be prepared to deal with quite different environments it can be in terms of the support, the services it can expect to be out there or not. So a little recap of how Flink works now in production. So the standalone mode is like this. You have a client. This is your application. And there's what we call the job manager, which you can think of as the master node, and a set of task managers, which are the workers where the jobs get executed. What happens in standalone mode is you need to start up a job manager, you need to start up a set of task managers. The job manager is configured to expect a certain number of task managers, and it waits until they all register themselves. After that's done, the client can come along and submit a job. The job manager will break that job up into tasks and feed them to task managers to get them executed. That's reasonably straightforward. But what happens when Flink is running on YARN becomes quite a bit. This is again the current status, which this is the broken way that we're trying to fix. So now instead of the client submitting a job, it's actually submitting the Flink application. And it submits that to the YARN resource manager, which in turn spawns an application master, which contains a job manager. And the application master starts up the task managers. And then from that point on, it's just the same story I told you before in the standalone mode. The task managers register themselves, the client submits a job, and the tasks get executed. There's a piece I left out, though, which is rather ugly, which is the client is polling. So it started off submitting the Flink application to YARN, and then it starts polling down here, waiting to hear that the job manager is actually ready to accept the job. That's unfortunate, but that's the way it works right now. After analyzing the situation pretty carefully, this is what we came up with to resolve these issues that we were wanting to fix. The task managers will stay pretty much the same that they've always been. The job manager becomes itself much simpler, and its responsibilities are being broken up into 3 separate services. The goal here is to have a much better separation of concerns and to make it much easier to adapt this collection of services to different environments. So the job manager now will only be responsible for one job period. And it's started up by the dispatcher. So the dispatcher is the point of contact for the client. It starts up a job manager for each job, and the job manager has much simpler responsibility. It just thinks in terms of the resources that task managers have. We call them task slots. A task slot can run one subtask of your job. And the job manager talks to the resource manager about its needs for task slots. So to sort of recap what I just said, in the simple case, the job manager requests slots from the resource manager. The resource manager knows how to start up task managers, and when they're ready, the job manager can deploy things to them. So how do we get back to what we... So this is the replacement for the diagram I had earlier, and this is working much better now. So what happens is what your YARN client submits is an entire Flink application. It's the job graph as before, plus all the jars that go with it, plus any credentials that are needed to run the job. If any of you are familiar with the sort of nightmare that can happen in Spark or Flink, when the workers need to dynamically load classes, you can end up with all sort of configuration nightmare. Having the jars come along with the job eliminates that problem. The resource manager receives all this stuff. It spawns the application master, which is a YARN construct, which holds inside of itself the job manager and the resource manager that's part of Flink. And the rest of this pretty much works in the same way I've been talking about before. And how is this different? As I mentioned, this has advantages in terms of making it simple to get the classes loaded properly. We can do much better sort of containment of security credentials. We can dynamically allocate and free slots while the job is running. And the client becomes a much simpler thing that just submits the job and then is done. It can just go away at that point. It doesn't have to wait until the job has been started to run. Now what becomes interesting, yes?
Question, how are the jars deployed? Is this, are they all together in one kind of package that has to be transmitted to every node, or are they kind of taken from a main repository or something like that and cached, or is that?
That's a good question. I don't know, actually.
Is it a YARN specific thing, or is it Flink specific?
I don't know. Sorry. So one of the things we get as a benefit from this re-architecture is it becomes much easier for us to decompose and put the pieces together in different ways. In this solution I showed you, the application master could hold both the Flink-YARN resource manager and the Flink job manager, but it's also possible to split those apart into separate processes if that seems advantageous, and it might be because YARN only allows one application master, but you might want to have a hot standby for the job manager running, for example. And the diagram I showed you before was a way of replicating what we call YARN job mode, where you spin up a new YARN cluster for one job. If you're really more interested in a richer environment where you have lots of jobs running and maybe sessions that span multiple jobs, then you'll want to have a dispatcher involved that knows how to start up individual instances of this for each job. And then the story for Mesos becomes basically the same story. And the only piece that really has to significantly change is this dispatcher. We need to have a Mesos-aware dispatcher instead of a YARN dispatcher. And we need to have a Mesos-aware resource manager instead of a YARN-aware resource manager. But the rest of the pieces can just be reused. We can also rebuild the standalone story in a very analogous way. Here what we imagine is, and I say imagine because we haven't really done this yet, I think, two kinds of processes, the Flink master process and task managers. And the master process can hold a very simple dispatcher, the job manager, and a very simple standalone resource manager. This resource manager is just accepting the task managers that register themselves. It isn't clever enough to or needing to start them on its own. And then what does Flink on Kubernetes look like? Similar to what I just showed you, we can have two kinds of containers, worker containers and master containers that hold the client and the job manager and the resource manager all in one process. Yeah. So to wrap this up, there's really a zoo of different cluster management solutions out there, and what makes this challenging is that they offer different abstractions, different paradigms. And so it's really not feasible to have sort of a one-size-fits-all solution. We need to have a set of building blocks that we can compose in different ways to fit the needs of different environments, and that's what's happening. This is ongoing work, as I said, in collaboration with Alibaba. As soon as we released 1.2 a few weeks ago, we merged the Flip6 branch into master, and so all of this stuff is now in the 1.3 snapshot. But it's sort of held off to the side where you don't experience it unless you choose to work with it. The goal for the 1.3 release is, roughly speaking, to get the standalone and YARN stuff running well. So in conclusion, there's lots of interesting stuff in Flink 1.2, and I only talked about a couple of pieces of it. And I've given you some look at where we're going in the future, which really is oriented around being able to do what I think everyone wants, which is to dynamically scale up and down Flink jobs while they're running and have it just work seamlessly. Let me just mention that we're hiring. In particular, we're always looking for software engineers, who are the people who work on the Flink platform and our products. And we're also always looking for data engineers, who are the people who help our customers be successful with Flink. We also have 2 annual conferences, one in San Francisco and one in Berlin. And urge you to attend if you can, and if you can't, please watch the videos. They're all online. And very happy to announce that my colleagues Fabian and Vasily are writing a book, and the early access version O'Reilly just became available today, so we're excited about that. So check it out if you're interested. And with that, I'm happy to take more questions about anything related to Flink.